Welcome to Chapter 3 of UV Spectroscopy, where we will explore the Woodward-Fieser rules for structure determination. Today, we will learn how substituent groups affect conjugated structures and how these effects can be quantified using the Woodward-Fieser rules for three specific chromophores: conjugated dienes, conjugated denones, and aromatic systems. For acyclic butadiene, two conformers are possible: S-cis and S-trans. The S-cis conformer has a higher potential energy, resulting in a lower energy, longer wavelength transition for the HOMO electrons. In butadiene, pi-to-pi transitions can occur for both S-cis and S-trans conformations. The S-trans conformation is more favorable, leading to an intense absorption at 217 nanometers, while the S-cis transition is typically forbidden. The pi2 to pi3 transition in butadiene is observed as an intense absorption at 217 nanometers. This band is insensitive to solvent, and is influenced by alkyl substituents and further conjugation. Woodward and Fieser conducted extensive studies on terpenes and steroids, leading to the development of rules for predicting electronic transitions. These rules were later distilled and expanded by Scott and Rao. The Woodward-Fieser rules for dienes start with a base value of 217 nanometers for acyclic butadiene. Incremental contributions from substituents are added to this base value to determine the final lambda max. For example, isoprene has a base value of 217 nanometers with an additional 5 nanometers for one alkyl substituent, resulting in an experimental value of 222 nanometers. Allylidene cyclohexane has a base value of 217 nanometers with increments for substituents, resulting in 237 nanometers. Cyclic dienes have two major types: heteroannular, transoid, and homannular, cis-oid, each with different base values. The increment table for cyclic dienes is similar to that for acyclic butadienes. In the pre-NMR era, the Woodward-Fieser rules were crucial for discerning isomers, such as abietic acid and levopimaric acid, based on their UV spectra. For example, 1, 2, 3, 7, 8, A hexahydro 8A methylnaphthalene has a base value of 214 nanometers with increments for substituents, resulting in an experimental value of 235 nanometers. Heteroannular and homannular dienes have different base values and increments for substituents. For example, a heteroannular diene with 4 alkyl substituents and 1 exocyclic double bond has a lambda max of 239 nanometers. Common errors in assignments include misidentifying the type of diene. For example, a compound with 3 exocyclic double bonds should not be classified as a heteroannular or homannular diene. Carbonyls have two primary electronic transitions, N to pi and pi to pi. The N to pi transition is allowed but lies outside the routine UV range, while the pi to pi transition is forbidden but can be observed. For carbonyls, substituents can cause hypsochromic shifts in the N to pi transition. This shift is due to the inductive withdrawal of electrons, making the carbonyl oxygen more firmly held. When the C=O system is conjugated, both N to pi and pi to pi bands are orthochromically shifted. The shift is more pronounced for the pi to pi transition, especially with longer conjugated chains. The molecular orbital diagram for a conjugated enone shows the effects of these transitions, highlighting the energy levels and transitions involved. The Woodward-Fieser rules for enones provide base values and increments for various substituents, allowing for accurate prediction of lambda max. Aldehydes, esters, and carboxylic acids have different base values than ketones. These differences are accounted for in the Woodward-Fieser rules for enones. Unlike conjugated alkenes, solvents affect the lambda max of enones. The Woodward-Fieser rules also describe these solvent effects, with specific increments for different solvents. Enuns are more complex than dienes, with specific cyclic enun values and experimental values provided. The Woodward-Fieser rules help in determining these values. Using UV spectroscopy, we can discern between isomers like erymophilin and oloerymophilin. Problem sets help in understanding these concepts better. Aromatic rings are widely studied due to their complex absorptions from various electronic transitions. Benzene, for example, has 6 pi Mos, 3 filled and 3 unfilled. Benzene's transition energy states are illustrated, showing the possible HOMO-LUMO transitions and their corresponding wavelengths. The allowed transition is not in the routine UV range, while the forbidden transition is observed with substituent effects. Another forbidden transition is noted at 260 nanometers. Substitution, auxochromic, conjugation, and solvent effects can cause shifts in wavelength and intensity of aromatic systems, though these shifts are hard to predict. Groups attached to the ring with unshared electrons can induce shifts in absorption bands. Non-bonding electrons extend the pi system through resonance. The presence of n electrons allows for n to pi transitions, leading to a charge transfer excited state when the electron is removed from the group. pH changes and protonation/deprotonation of substituents can alter the energy of transitions, affecting the primary and secondary absorption bands. Substituents capable of pi conjugation interact with the benzene pi system, causing shifts in the primary and secondary bands. Electron donating and electron withdrawing groups influence the primary absorption band, with donating groups increasing the lambda and epsilon of the secondary band. Tables show the impact of various substituents on primary and secondary absorption bands, highlighting the differences between electron donating and withdrawing groups. For desubstituted aromatics, both groups' effects must be considered. The combined effect can be greater than the sum of individual effects. Empirical correlation of structure with observed lambda max is developed for substituted benzoyl derivatives, though it's less accurate than Woodward-Fieser rules. Tables show the substituent increments for various groups, helping in predicting the lambda max for desubstituted and multiple group effects. Polynuclear aromatics show increased lambda for primary and secondary bands with more fused rings. Heteroaromatic systems have unique spectra due to n to pi transitions. The visible spectrum from 400 to 800 nanometers is observable to humans, with adaptations for seeing color at the expense of detail. White light passing through or reflected by a surface shows complementary colors, leading to the concept of the color wheel. Colored organic compounds have extensively conjugated systems. Beta-carotene, for example, absorbs at 455 nanometers, showing the complementary color of orange. Lycopene and indigo are examples of compounds with specific absorption maxima, showing complementary colors in the visible spectrum. One of the most common classes of colored organic molecules are the azo dyes. These dyes are characterized by their nitrogen-nitrogen double bond, often flanked by electron-withdrawing and electron-donating groups. The arrangement of these groups significantly impacts the dye's color properties. Azo dyes are prevalent in our environment, contributing to the colors we see around us. Examples include para-red, fast brown, and sunset yellow, which are used in various applications from textiles to food coloring. The vibrant colors of M&M's candies are due to various azo dyes. Each color, such as bright blue, orange red, and royal blue, is derived from specific chemical compounds used in food products. In biological sciences, azo dyes like Bibridge scarlet are used to stain tissues or cell structures selectively. These dyes help in visualizing different components under a microscope, aiding in biological research. In chemical sciences, azo dyes serve as acid-base indicators, changing color with pH variations. Methyl orange, for example, shifts from yellow to red as the pH changes, demonstrating the effects of pH on aromatic substituents. With these 3 chapters, we've covered the foundational concepts of UV spectroscopy. I hope you've gained a solid understanding so far. In upcoming chapters, we'll dive into more advanced concepts to deepen your knowledge. Thanks for watching, and take care. Goodbye.